We're recording. Okay. All right. So, starting with chapter 4, the first thing to know is not really, all these details per se, the numbers here, and not to memorize all of these different, either storage, places that store carbon or where it's moving around in the ecosystem. But maybe if you're familiar with some of these, it might be like one question that talks about the carbon cycle, as far as what are um, places that store it, pretty well, really, like these. If you know the three main reservoirs for carbon, in the atmosphere you have CO2, methane, carbon monoxide, and then carbonate based rocks predominantly, and then plants and animals, like our building blocks. Um, those, that would be good to know, these three at least. And then, so that's all really the black things in this figure. So just these reservoirs. And then, I guess, being familiar with, the deforestation releases carbon in the form of CO2. Reforestation then sequesters CO2. So, some of the things that kind of sequester carbon, like photosynthesis, reforestation, um, and then things that kind of get rid of it, like burning forests or, oops, what happened? There we go. Or respiration, for instance, like photosynthesis, the process of respiration. So just kind of, not memorizing it per se. I'm not going to have you draw this, but, be prepared for just some, multiple choice question related to this carbon cycle. Okay. This probably is not that important for the exam, knowing these numbers. And so I guess then the big first content piece was related to naming. So last day, on Monday, we talked about, naming hydrocarbons and molecular compounds, non-metal with non-metal. Now it's going to be ionic compounds. And so that's, a metal plus non-metal or more. Okay. I guess there were two varieties. So there are the main group compounds. And so this is if you have a metal that is in groups really 1, 2, let's say 13 or 14, some of these bottom ones. So these are nonmetals up here, but as you go down, like tin and lead, those are also metals. That also though. Yeah, let's just say actually 1, 2, and 13. Okay, so the naming for that is we really know what charges the metals have, so you don't use Roman numerals. Okay, and then again, don't use prefixes for anything either. Okay, so remember that would be, if it's this, that's just going to be, I guess, the name for that one, instead of me jotting it down here. So the name for that, and then let's do another one. How about that one? Okay, so that first one, yep, just sodium bromide, yeah. So it's just the metal, and then whatever the nonmetal is with an IDE suffix. So that's sodium bromide. And then this one, Al2O3. Yeah, just aluminum oxide. And some, it's all going to be multiple choice again, so some of the other answers will be like aluminum 3 oxide, so that wouldn't be right. Or like dialuminum trioxide will be there too. Okay, so remember, for any of these ionics, including this group, the middle transition metals, fight the temptation to use those prefixes. Never do like a di, tri, those ones. Okay, never do that. Okay, so that's really the first variety. Going backwards, I guess. So if you have like this one, is I don't know, maybe it's easier. Some people think it's harder. But in this case, or I guess the other way around, right? To go from the name to the formula. So let's say it would be rubidium nitride. Okay, so I think, yeah, this is probably the harder way to do it. What is the formula for this name? The strategy here is to write the ions, right, with their right charges. So rubidium is Rb plus, okay, because it's in group 1. And then nitride, what would be the charge of nitrogen? I guess it's on the slide, isn't it? So, yeah, N3 minus, okay. And so with that, what is the formula for rubidium nitride? Yeah, so it would be Rb3N, right? Because everything has to equal a 0 charge. Okay, so that means that you have like 3 times a plus 1. So that's plus 3, and that will equal the minus 3. Okay. All right, so any questions about that first type of compound? Okay, for any of these, as we're going today, if you want me to do more questions on any topic, just, shout it out or type it in the chat box there. Okay. So then the second variety are the transition metal compounds. Okay, so these have variable oxidation states. I guess transition metal compounds plus tin and lead. Okay, so those are these ones here. Okay, so basically whatever is in pink here. Okay. There are some transition metals that we kind of know their charges, but even some of those, I think, for this level, if we just say anything in this block, put Roman numerals as well as these two. Okay. So yeah, so these ones you're going to need Roman numerals, to indicate the metal charge. And again, no prefixes. Okay, so examples of this. My iPad is frozen. It would be this one, for instance. Okay, so what would the name be for this? Let's see. We can get it back. There we go. So TiO2. And then let's do one like this. Let's see. That. And then okay, so let's do those. So TiO2, this one first. So what's the name for that? Yeah, correct. Yeah, this is titanium 4 oxide. And the reason that it's 4 is because oxygen has a -2 charge. It's 2 away from the noble gases. Okay, so if this is -2 and you have 2 of them, that's a -4. So the metal, you just have one of them here, has to be +4. Okay, so titanium 4 oxide. Okay, now this one, and you don't have your periodic table with the names in front of you, so that is manganese. Okay, so what do you think? Yeah, manganese 3 oxide. Okay, so it's -2 times 3 is a -6. So this whole other side has to equal +6. And you have 2 of them, so it's like 6 divided by 2. Each of them are +3. Okay. All right. And then the last one here is going kind of the other way around. Now this is definitely much easier, I think, to go to the formula. So copper 1 oxide. Okay, so yeah, Cu2O. Okay, so that means that so oxygen -2, and so this whole other side has to equal +2, and so that means that each of the coppers are +1. Yeah. Okay, so in other words, I guess you could say this, really. And then oxide. Okay, and then look at, that's a -2, so then how many of these do you need to get a +2? And so it's 2. Okay, so any questions about this variety? Okay, so again, if you have something like this, or any of these with tin and lead, even though they're not in this middle group, you still need Roman numerals. Okay, so this would be, what is it, tin 2 chloride. Okay, and then this one would be lead 2 oxide. Okay. All right, so naming ionics. And then, there's some examples here for you. These polyatomic ions, you have a couple pages of paper to write your notes on. So this would be something I would suggest you jot somewhere on your couple, both sides of your 8.5 by 11 paper. These names. You don't need to include really any others. I will stick to only these ions. But you could have some questions like, let's do a complicated one. What about this? Well, I guess just that. Okay, so what do you think the name for this is? So MnSO4. Yeah, manganese 2. Yeah, and so it's recognizing each of those, the sulfate is 2 minus, and that has to mean that's 2 plus. So yeah, so manganese 2 sulfate. Okay. Some books would call it this too. I'm not going to, obviously, on the exam pick, one or the other, but okay. So that, and then what about going this way? This is definitely harder. So calcium, if I go back to here, calcium has a +2 charge. Nitrate is NO3 minus. Okay, so then that means if you put both of these together, you're going to need 2 of these, right? Because you have a +2, so you have to get a -2. And so that would be CaNO3 2. Okay, so calcium nitrate. All right. All right, and there's only one complex ion here that's a positive one, so ammonium. All the others are negatively charged with, either -2, -3, or just minus. Okay. All right, then we talked about, this kind of is an extension from like chapter 1 when we looked at, atomic weights. And so, for instance, if you look in the periodic table for carbon, you'll see this, okay, in its little box. Okay, so that's your atomic number. That last day we said is, number of protons, number of electrons for neutral carbon. This number is the atomic weight. Okay. And so I guess, some books will call it the atomic mass as well, I guess. So sometimes you'll see it as atomic mass. But this number is, again, the weighted average of all the isotopes. In this case, carbon isotopes, right? So if carbon has, carbon 12, carbon 13, and carbon 14, okay, then you've got, their relative abundances here. And so to calculate it, you just really do the weighted average. So it's, 98.9% of 12. So it's really 0.989 times 12. Okay, plus 1.1% times 13. Okay, this is the unit for, it used to be AMU, and now it's just U, this unified atomic mass unit. Okay, and then we do the percent of carbon 14. So what is that? 0.001%, so that's 0.00001 times 14. I think, yeah. Okay, so if you add up all these terms, then you should get 12.01 U, okay, or thereabouts, okay? So 12.011, I guess. Okay, so a question might be where, you're given percentages and what their mass numbers are, or what isotopes they are, and then, what is its atomic mass or atomic weight. Okay, so you would just do the same procedure and then add up everything. Okay. All right. And so we then got into the mass number and dealing with like moles here. So the next concept then we got into kind of hardcore as hardcore as we got this semester really with math. And it really boiled down to this. So this would be something else I would suggest maybe putting on your note card there. Okay, so if you have moles in the middle, if you're going away from moles to something else, you're multiplying. To get back, you're dividing. Okay, and then in this case, going from moles to grams, that's times the molar mass or molecular weight. Okay, and in this case, it's Avogadro's number. Okay, so if you have then 12.01 grams of carbon, you're starting here, and you want to know how many moles is that. You're going to divide by 12.01 grams per mole, so that equals 1 mole. Okay, so if you have 36 grams, you're just going to be dividing by 12, and that'll give you 3 moles. Okay, so that's going kind of between grams and moles. And then if we want to know how many carbon atoms are in 36 grams, okay, so in that case you're starting here. We have to first go through so many moles, and then from moles we then will get the number of atoms in this case. Okay, so this, remember, could be atoms, it could be ions, molecules are the 3 kind of big ones there. Okay, just depends how the question's worded. And so here it's 36 divided by the 12, so you have 3 moles, and then you multiply by Avogadro's number. Whoops, 23rd. Okay, so something else you should kind of include in your notes there. So Avogadro's number, so that's 3 times 6.02 e to the 23rd. So that would be 1.81 times 10 to the 24 atoms, carbon atoms. Okay? So all of those, there'll be a few questions related to this, going from moles to grams or vice versa, or number of something. Okay, so if you're given like, 5 oxygen atoms, okay, read the question really carefully too. If it says oxygen atoms, it's just this, right? If it says oxygen molecules, it's this. Okay, or elemental oxygen. Okay, it's also O2, not just O, right? Okay, so if you have 5 oxygen atoms, now you're starting here. Okay, so you're going to divide by Avogadro's number to give you moles, and then you're going to multiply by the atomic weight, in that case, or atomic mass. Okay, so it would be 5 divided by 6.02, 10 to the 23rd, so 5 atoms, oxygen atoms. So that would be 5 divided by 6.02 e to the 23rd, so that's 8.31 times 10 to the minus 24 moles of oxygen atoms. And then you're going to multiply by 15.9994 grams per mole. Okay, so then the moles go away, and you end up with so many grams. So that's 15.9994. So 1.33 times 10 to the minus 22 grams. Okay, so if you have just a small number of atoms, remember this number should be insanely small. Okay. All right. And again, I just used it for oxygen as it was in the periodic table. If it were this, it would be then 30. Right? You'd need 15 or 16 times 2. So I guess it's 32. Right? Okay. Any questions about that? All right, so yeah, so this here. So there will be some questions, related to what is the molar mass of something too. So just like I had on earlier exams. Okay, and you just add up all the atomic masses. Okay, so if it's this, so sugar here, you would just do, 6 times 12, 12 times 1, and then 6 times 16. Okay, and add up all that, and that's your molar mass. Okay? All right. Then, we got into some calculations then. And so, the types of questions you'll get on the exam will be based on, like balanced equations or equations that may not be balanced. So for instance, here's one that could be typical. Okay, if you have 5.5 grams of hydrogen, how many grams of water do you produce? Okay. And so for this, what is your first step always in these calculation questions? Yep, always balance. Okay, never assume any equation on your exam is balanced as is. Even if you see a number in front of something, don't assume it's fully balanced, okay? Yep, so always balance. So in this case, that would be what then? So we got 2, so I guess 2 there and 2 there. Okay, so then what's your second step? So your red flag in these questions is if you have grams of something, you can convert that to moles. Oops, where is it? Is that far away? Right? So if you have grams, you can go to moles. Okay? So for that, how do we calculate moles of hydrogen here then? So you have 5.5 grams. Okay, and I'll go back to this little thing there. Okay. So you're here, and you want to go to here. Yeah, so you're dividing by molar mass. So that's 5.5 grams divided by the molar mass of this. Okay, don't put this 2 in there yet. So that's, each hydrogen is 1.01, so it's divided by 2.02 grams per mole. Okay, is equal to, so 5.5 divided by 2.02, so that's 2.7 moles of hydrogen. Okay, so how many moles of water do we have then? So this is where now you are looking at these numbers. This is the only time these balance coefficients really come into play. Okay, what you're given and what you don't know here. The water is what you're trying to solve for. So you're just looking at how these compare. So it's a 2 to 2, right? So that means, therefore, so it's a 2 to 2 relationship, so you have 2.7 moles of water. Yep, so yeah, so 2 to 2 means 1 to 1, yeah, it's the same thing. Yeah, if it's that same number with 3 to 3 or 5 to 5, yep, so it's the same, okay? So 2.7 moles of water, and then our final step then, we want to know grams. of water. So then you're going to multiply by its molar mass or molecular weight, right? So that'll be 2.7 moles times 18 grams per mole. Okay, so that's an oxygen and 2 hydrogens. Okay, so then that gives you 2.7 times 18. So 48.6 grams of water. Okay. All right, so on the exam, I think I mentioned the concept of limiting reagents, in class. I'm not going to muddy the waters on the exam with questions related to that. So this is very typical of what you will see next week. Okay, so I'm not going to give you, 5.5 grams of each of these and then ask how many grams of water. And then you have to figure out which one do I use here. So there you'd have to determine what's limiting, and that gets into a whole can of worms. So the ones you'll get on the exam, you'll only be given grams of one of the reactants, and the other one you assume is in excess. Okay, so you don't, who cares about oxygen here? Okay, so that really is helpful because whatever you're given grams of, that's what you need to convert to moles. And then once you have moles, just look at those balance coefficients to get moles of anything else. Okay? So any questions about that? Okay, it doesn't have to be like a reactant to go to a product, but it could be asking like how many grams of oxygen do you need to react with hydrogen. So then here you would do moles of this, and then you'd have to divide by 2 because it's a 2-to-1 ratio, and then you get moles of oxygen, and then you can do grams of oxygen. Okay, so you can go basically between anything else. It could be reactant, it could be products, but just whatever the question's asking. But your starting place is always whatever you're given grams of. That's your red flag there. Okay. Okay. This figure is really busy, so I'm not going to ask anything related to this figure per se, but you should know what the greenhouse effect is. I think there was a question on one of your midterms, so I might even recycle that same one, that, in words kind of describing what the greenhouse effect is. It's really just, there is a natural balance, okay? So the greenhouse effect, it's worthwhile noting. So this is something maybe that gets lost in translation here, because we're always talking about, climate change or global warming kind of thing. And we say that, it's due to the greenhouse effect. So people have the conclusion that the greenhouse effect is bad, but it actually is not. So the greenhouse effect is a natural effect, and is needed for life. Okay. Okay. So this greenhouse effect is really what gives us this average temperature of Earth of 15 degrees Celsius. It's actually going up in recent years on average, but we aren't at minus 18, most of the time, in other words, because of this. And it's really that, sun hits the Earth's surface, and then you've got this natural atmosphere that blocks some of this heat from escaping. So it's really infrared is what we're talking about in this chapter. Okay, so the previous chapter was UV. Now we're talking about heat or infrared radiation, so less energetic radiation. And instead of this breaking apart bonds, now it's, for instance, CO2 or water. Okay, now instead of these bonds being broken, it's actually just like vibrating or bending. Okay, so it's bond stretching or bending is what happens when IR radiation is absorbed. So kind of knowing what the greenhouse effect is and what happens to molecules when IR is absorbed versus UV is absorbed. So UV radiation would actually break this apart. Okay, so you'd have like OH plus H, okay, with UV. With infrared, you don't break bonds. Okay, so hopefully that makes sense. So be ready for those kinds of questions. In general, what is this? And then what happens as we put more greenhouse gases in the atmosphere, right? So this is just based on kind of an average concentration of CO2, but what happens if CO2 goes up over time? Then we're going to trap even more infrared radiation. And so heat, it's more heat in this troposphere, okay? All right, and then knowing what are gases that can absorb infrared radiation. So two that are most prevalent in our atmosphere do not absorb IR. Okay, and so remember, for infrared radiation, you have to have the molecule undergo a change in its polarity. Okay, and so remember, and we're going to talk about this later today too, molecular polarity. So the polarity of a molecule is where you can have, like this side of the molecule be negative slightly, that would be positive. Okay, and if it's the same atom, you can't do that. You can't draw that, one side's going to be more negative than the other. And so since you don't have any change in polarity, then they can't absorb infrared radiation. So it's ones like this, where now you have, this set up where oxygens are more electronegative, so those are the negative ends. This is more electropositive. And so now what happens is you can change, the asymmetric stretching. Okay, so this slide right here is pretty key. Okay, so that'd be one that you can, I don't know, even maybe do a little sketch on your notes if you want, or just kind of look at this and remember it. That the symmetric stretching, this is CO2, so that's carbon, those are the two oxygens, and it's linear. If both of these are being stretched out at the same rate, then nothing is changing. These dipoles, or the charge on this molecule, is not changing, right? But if, let's say, these come in closer, whereas this goes farther away, now you are changing the overall charge distribution of this molecule. So this would absorb IR, as well as this. If you're bending, okay, that's also going to absorb this one. Okay, so all of these other ones would absorb IR, but this mode does not. Okay, so any of the symmetric stretching, so we call it symmetric stretching, is not responsible for infrared absorption. Okay. All right. So, yeah. So I guess with that came different shapes of molecules. Okay. So this is the key table to know for the exam. Okay, so knowing what type of molecules are linear, bent, trigonal planar, trigonal pyramidal, or tetrahedral. So those are the only geometries or shapes that we're going to look at this semester. Okay, so any of the questions on the exam will have to have those shapes. Okay, so things like, PCl3. So what's the shape of PCl3, for instance? What I'm telling you is implicitly you have to first draw its Lewis structure. Okay, and so like that. Okay, and then you recognize that it's what we called AX3L. Okay, where you have three things bonded to it, three atoms bonded to the central atom, plus a lone pair. Okay, and so that means that it is trigonal pyramidal. Okay. All right, and then really not knowing exact angles, unless it's linear, you're like CO2. If it's linear, that's an easy one. So that's 180 degrees. Okay. You don't have to really know. A tetrahedron is 109.5 degrees. You don't have to know that. But if I have a question where, you've got, if I tell you that's tetrahedron, and then you have this, if you replace this with a lone pair, for instance, if you replace a bond with a lone pair, what happens to these angles? Do you remember? So what do you think? Is it going to be greater than 109.5, less than, or equal? What do you think? So here, that's your lone pair. So anytime you replace a bonding pair of electrons with these non-bonding lone pairs, you now have more repulsion between this lone pair set of electrons and the two electrons here. So the angle will always be less than what it was. Okay, so it's going to be less than 109.5. Okay. All right, so yeah, we saw this really in action here, right? Where now, I guess this is not showing it explicitly, but there were two lone pairs off of here. So now it's 104.5, so it's gone down significantly. Okay, whereas one lone pair, it's kind of 117. So this used to be trigonal planar. Okay, so remember trigonal planar is kind of an easy one too. So all those are 120 degrees. Okay, so it started off with 120. If you do this, okay, replace it with a lone pair, now it's going to be less than 120. And it's, about 117 here. Okay. Yeah, this is, I guess, what I was talking about before. So UV breaks bonds, infrared vibrates individual bonds. It doesn't break them. And in microwave, we mentioned it in class. We didn't have any applications from it, but it just rotates. So it doesn't even have enough energy to vibrate the bonds. Okay. Yeah, you should know about electronegativity, like what its definition is. And so the most electronegative element is fluorine. Okay, so just always look, is it closest to that top right of the periodic table? So electronegativity increases as you go, bottom to top of a group, or it increases as you go left to right of a period. Okay. And then, kind of just to piggyback on that, so this then really, from chapter 5, when we started talking then, I guess chapter 5 and chapter 8, when we really were talking about intermolecular forces, right, is where we then looked at this electronegativity in individual molecules and then decided whether a molecule was polar or nonpolar. Okay, and so let's kind of talk about that here, since we're talking about it, electronegativity now. So is the molecule polar or nonpolar? What you have to do is draw again its Lewis structure, figure out its shape. Okay, so it's going to be either one of those 5 shapes, trigonal, planar, whatever, and then figure out the I guess draw bond dipoles in your molecule. Okay, and so let's just do an example as we're talking here. So let's say boron trichloride. Okay, that would be its Lewis structure. Its shape is going to be trigonal, planar. Okay, and then out of boron versus carbon or chlorine, which is more electronegative? I don't know if I have a periodic table in here, maybe earlier. Right here. Yeah. Okay, so boron's not shown here. Yeah, so boron's here, chlorine's there, so definitely chlorine, much closer to fluorine, right? So since chlorine is more electronegative, then that means that you're going to have, these are going to be more negative. Okay, that's going to be more positive. Okay, and the way we would kind of indicate that was, remember these little arrows. So they're pointing toward the more electronegative atom. Okay, and then I gave you a table, it's in your notes, of the geometries that cancel each other as long as all these are the same around the central atom. And this was one that if everything is the same, then these cancel. Okay, so in the tug of war, if you will, between all these arrows, you're not moving the boron any direction. They're all going to cancel. So you would say that the bond dipoles cancel in BCl3. Therefore, what do you think? Polar or nonpolar? Yeah, so yeah, somebody already read my mind. So yeah, so it is nonpolar. Okay? So as soon as you do one of these numbers and say, okay, instead of chlorine, now let's say that iodine, okay? It's no longer going to cancel because you'd say that this arrow, iodine is more electronegative, but it would be maybe like that. Okay, so it's not as different in electronegativity between these two. So now you've got something pulling that hard, that's the same magnitude, and now you got something just a little bit here. So they don't cancel anymore. So now this, so what is that? BCl2I would be polar. Okay, because they don't cancel one another. Okay, so there is the difference then between bond dipoles. That's just these little arrows between individual bonds, and whether you have so molecular dipole, if you will. Okay, so that means adding up kind of, or thinking about all those bond dipoles, do they cancel or not? That's how you get whether the whole molecule is polar or nonpolar. Okay, so is everybody kind of cool with that concept? So, water was polar again because these were your little dipoles. Okay, and they're not 180 degrees from one another, right? So they don't cancel, so therefore polar. Okay, if water were linear, then they would cancel. So this is nonpolar. Okay, and we said that, we'd all be dead if that were the case. Okay. All right, so between polar, nonpolar, and then what we did was figure out then between these molecules what intermolecular forces exist. So between two waters, how are they held together? So this is an intermolecular force. Okay, and we looked at three varieties: London dispersion. Okay, and those are between nonpolar. Okay, so look for, hydrocarbons, for instance, are great varieties of that. So, in chapter 5, um, all of these, if I go to that slide here, there we go. If I can blow this up a little. All these hydrocarbons that you know the names of, remember those were like butane, pentane, hexane, heptane, all those with, meth, eth, prop with an A and E. They're just these structures, and so each of these carbons, it's not immediately obvious that all the dipoles cancel. But if you look at this carbon, for instance, it's surrounded by two other carbons, so you can think about it, is it kind of in the tug of war, those cancel, and then these would cancel. Okay, it's not really 90 degrees like shown. These are all tetrahedral, but you can roughly think about it like that. Okay, so any of these will cancel. Okay, and so even this carbon, you've got three hydrogens plus a carbon. So that one really wouldn't cancel, but then you've got one with that same environment at the other end of the molecule. So both of those still cancel. Okay, so all these hydrocarbons, they would just have London dispersion forces, okay, that hold them together. And the rule there is as you increase molar mass, then you increase the London dispersion force. Okay, so as you go down here, notice what happens to the boiling point. Okay, so boiling point means, how hard is it to break apart two of these molecules. So this one connected to the next one through these London dispersion forces. So here it's only minus 161 degrees is enough to break these apart. As you get more molar mass, you see that this goes up and up, right? So that means that it takes more energy to break apart heptane than it does methane. Okay, so increasing molar mass means increasing London dispersion, and then that means that you have an increased boiling point or melting point if it's a solid. Okay, so those are when you're melting something, when you're boiling something, the intermolecular forces are really what you're breaking apart. You're not breaking apart bonds themselves. Okay, so that was the first variety, so London dispersion. So that's all nonpolars, okay? And then the next one was dipole-dipole. Okay, so that was between polar molecules. Okay, and then we had really like, I don't know, a subclass of that, which was hydrogen bonding. Okay, so those are also polar, but it's between very polar molecules. Okay, and in that case, hydrogen bonding is if you have OH, an NH, or an FH in your molecule. Then it's hydrogen bonding. If you have anything else, then it would be dipole-dipole. Okay, so for instance, this would be a hydrogen bond. This, did I do that? Whoops, I did that totally wrong. Should be the H. Whoops, Cl. Okay, so, there we go. This is a dipole-dipole, or dip-dip, I'll say here. Okay. All right, so both of these, these are polar molecules, all of them, okay? But if you have an H that is not a nitrogen, oxygen, or fluorine, now it's just dipole-dipole. Okay? So here's a very common example of another one that would be a hydrogen bond. Okay, between ammonia. Okay, because you've got an N directly bonded with hydrogens. Okay. All right. So any questions about those three intermolecular forces? Do you want any more examples? So CO2, for instance, that's nonpolar, right? Because it's linear. So these would be connected, if we do it maybe like that, by London dispersion forces. Okay. So something to be aware of, for your future teaching, if you ever get to this level of teaching in your schools. Most of you probably will never, but you never know, is that everything actually has London dispersion forces. Okay, so it turns out, even these ones, that have dipole-dipole, they have London dispersion as well. But it turns out that, these are so much stronger. We kind of don't even really talk about London dispersion. We just say, yeah, it's either dipole-dipole or hydrogen bonding. Okay, so water, for instance, even water, really, will have London dispersion and hydrogen bonding is probably the best way to fully describe these intermolecular forces. Okay, but we tend to forget about London dispersion in water just because hydrogen bonds are so strong. Okay. Okay. So types of questions would be maybe asking what intermolecular forces are between certain molecules, asking relative boiling points, for instance. So if I give you, here's a question for you. Okay. Let's do this. Okay. So rank these in order of increasing boiling point. Okay, so what I'm telling you in this question really, or what I'm asking you in this question is rank these in order of increasing intermolecular force. Okay. And so what you have to do is kind of go down the list and figure out what are polar, what are non-polar first. Okay. And so argon is held together by what type of intermolecular force? So in that case, all you have are just individual argon atoms. It's not even a molecule. So it's just argon atoms. And so there's no, difference in the molecule between, one side of the molecule's positive, the other's negative. So if it's just an element like this, you assume that it is just with London dispersion forces. Okay. And then CO2, we did that above, right? So that is nonpolar, so therefore London dispersion. Okay. Water is polar, very polar, I guess you'd say. It has an OH involved, so that would be hydrogen bonding. And then this is polar, and it doesn't have an H connected to an O, N, or F, so that's just dipole-dipole. Okay, so what do you think? So argon, let me pull up a periodic table here. So you can see the molar or atomic masses here. So the molar or the atomic mass of argon is 39.95 grams per mole. Okay. And then CO2 is like 44 grams per mole. Okay. And so the others, we really don't care so much about molar mass, right? So London dispersion is all based on, the more molar mass, the more, the stronger the London dispersion force is, okay? Especially if the molecules are similar, but, for these ones, you can assume, it's a similar trend here. Okay, so with all that, what is your ranking then? What is going to have the lowest boiling point? So that means the weakest London, or the weakest intermolecular force. Yep, so argon, exactly. Yeah, so remember the trend. I think I did this in one of my videos. The order is going to be London dispersion, and this is in general too. So London dispersion is less than dipole-dipole, which is less than hydrogen bonding. So for those three. Okay, if you had, remember there was ion dipole as well, where you have, like, for instance, this. So that's a polar molecule with an ion. That's going to be even more. Okay, so ion dipoles up here. Okay. But yeah, so London dispersion is going to be the weakest force. And then you have to kind of go, you have two that have London dispersion, so you're just looking at their relative masses to see which one is lower. And so that's why argon then is less than CO2. Okay, and then what? So then you're getting to the polar ones. And so then it's going to be HCl, yeah, and then water, okay, because hydrogen bonding is stronger than dipole-dipole. Okay, so a question like that could be on there. And then another variety of question, other than, just giving you a molecule, like, I don't know, like this one. What kind of intermolecular forces could it have? So you're going to have to draw its Lewis structure. So I think it's something like this. You've got, like, resonance forms. Okay, with all their arrows. And so this is going to be bent, okay, which means that these dipoles are not going to cancel, so it's going to be polar, and then that means it's going to be dipole-dipole. Okay, so a question like that is a variety. Or then another type would be to give you two substances and ask if they're soluble in one another. Okay, so like dissolves like. And so for instance, what do you think about those two? Water and methane. Are they soluble? Okay, so yeah, water bent, and that means it's polar. Okay, methane is tetrahedral, and so if you kind of look up here, you can see that all of these will cancel. It's not going to be 90 degrees, but still, if it's a tetrahedron, all these cancel, so that's nonpolar. Okay, so all these are going to be nonpolar. Okay, so that's going to be nonpolar. So you've got polar with nonpolar, so not soluble or miscible with one another. Okay? So a question like that could be on as well. Remember that if you have a salt, okay, so salts, where you have, in other words, a metal and a nonmetal, any of those ionic compounds, in other words, so ionic compounds, they are considered polar, like very polar, okay? And so they will be soluble in polar solvents then. Okay, so this would be yes. Okay. All right. So I think, I think I'm not going to ask any real detailed questions about the context pieces. So you can focus more when you're studying, on the content pieces. So don't worry about like reading the chapter so carefully, really to prep for the final and knowing, okay, about each of these figures. Being able to regurgitate stuff. I guess the big data piece, I guess, to be aware of is that, our current CO2 levels are higher than it's been, in the last, 800,000 years, really. Okay, so we're at higher levels now than we've ever been, and so, being aware that that is the case, that our temperature's higher than has been. Well, I guess it's going up. I don't know. It has been higher in the past, but it's kind of still following cycles. But you can say, be aware, I guess, that temperature and CO2 concentrations kind of follow each other. Okay, so there's a dependence between those two. But any more detailed conclusions, climate model conclusions, I'm not going to ask those types of questions. The Kyoto Protocol would be something to remember. Okay, it's just really to stabilize and reduce atmospheric greenhouse gases. So this slide is actually something to kind of remember. So to know about the Montreal Protocol and the Kyoto Protocol are the two big ones. So the Montreal and Kyoto. So this is about greenhouse gases. This is about CFCs. Okay. And then, the whole trading, cap trade, all that stuff, I'm not going to ask questions about. So you don't have to worry about that. It gets kind of complex. Okay. And then, I guess just in this last chapter, I'm really not going to ask much about, again, the applications per se, but knowing what a combustion reaction is. Okay, so you need a fuel oxidizer and then you get products. So the very typical example is a hydrocarbon plus oxygen, and in that case your products are going to be CO2 and water. Okay, so this is a classic type of combustion reaction. Okay, so I might put one on like this and ask, that plus, other examples of reactions, and ask like which one is a combustion reaction. Okay, so just look for one where CO2 and water are your products, and that tells you that it's combustion. Okay. Yeah, I guess the three sides of the triangle, so you need a fuel, oxidizer, and heat. So what you need for combustion would be something I could ask. What hydrocarbons are, and you, again, in the previous chapter, you've already named these. I'm not going to ask about these different representations, really, but yeah, you should know what a hydrocarbon is. And then energies, you can think of that little activity you did with the skateboarder there. So you had, difference between potential and kinetic energy. There's also thermal energy, which is really a type of kinetic. So you really only have two forms of energy, and you can convert from one to the other. Okay, so the first law of thermodynamics is that energy can neither be created nor destroyed, but it can be converted into different forms. Okay. So this slide with all the definitions, maybe work not so much, but what energy is and then what these kinds are, that's important. Okay. Heat versus temperature is also important definitions. Yeah. And then some units. I'm not going to ask you these conversions. So, you don't have to worry, except I might ask you a dietary calorie. How many joules is that equivalent to? And so remember that capital C, calorie, is 1,000 small c calories. Okay, so just, I guess knowing this, or this would be something that would be easy to put in your notes, really, that you could refer back to. Okay, so just knowing that, if I have a food label, and let's say it has, 250 calories, okay, then converting that to so many joules. Okay, so you'd have to, like 1 cal is equal to 4,184 joules, right? 4,184, okay? And so you could set up a little ratio, right? If one cal, capital C, is 4,184, and I have 250 cals, then how many joules? Okay, so you just multiply those. Okay, and I might ask you in terms of like kilocal or kilojoules, right? So then that means you just, so let's say this, if I carry this through, that would be 250 times 4,184. So that's a lot. 104,600. Okay, so 1,046,000 joules. Okay, or you'd say 1,046 kilojoules. Okay, so again, knowing these like metric units that we talked about last day. Okay. right. You should know the difference between endothermic and exothermic. So this slide is really important. So knowing that if heat is flowing into a system from the surroundings, that's endothermic. If it's flowing out, it's exothermic. And then knowing the difference between the signs. So if you have a reaction happening and you have plus 36 kilojoules per mole, this positive means it's endothermic. That means that it's absorbing that much heat. Okay, if it's minus 36 kilojoules or whatever, that's exothermic, and that means it's releasing that much heat. Okay, so that would be this situation. It's outputting that kilojoules. Okay. And then the only calculation here was related to bond energy. So figuring out what an overall reaction, whether it's endo or exothermic, based on what bonds are being broken, what are being formed. Okay, and so if we look at like the easiest example of this. Okay, the first thing you do, as always, you balance, right? And then I suggest writing the Lewis structures for everything on here. And if there's two of them, then draw two of them. Okay. Okay, so like that. And then just look in your table of data that I would give you. This is not something you have to, waste space on your note card for all these. I will give you these in the question itself. And then you just look at this and say, these are all going to be broken, so they're going to be positive. This is going to be formed, that's going to be negative, so exothermic. And so then you've got, two HH bonds, so it's going to be 2 times plus 436. Okay, and if we look at units here, you have really 2 moles, and then it's that much kilojoules per mole. Okay. And then you've got 1 O double bond O, which I guess I don't even have on this form, but I don't know, like 798, I think, kilojoules per mole. Okay. And so those are all the ones that are being broken, so they're positive. So you would say then, so 2 times 436 is 872 plus 798. So that's going to be plus 1670 kilojoules. Okay, and then you do the same for this side in case, in this side they are being formed, so they're going to release heat. Okay, and so there's 1, 2, 3, 4 OH bonds, and so that's 467 minus 467 because they're formed. Okay, so that gives you 4 times 467. So minus 1868. And then you just add these up. Okay, so overall, it's going to be minus 198 kilojoules. Okay, so exothermic reaction. Okay, so that's really the only calculation from this chapter. Okay, and so this kind of walks you through. Okay, I guess I was way off with my O double bond O. Okay, so, but yeah, I would give you those values on an exam. Okay, and then as far as the rest of this, I wouldn't worry about that. It does talk about boiling points and London dispersion forces here. It's kind of a background there, but okay, so that's the whirlwind tour. Any questions? Anything you want me to go over more? Yeah, so the rest of today I will be finalizing your exam. So as I said, it'll be like around 50, 55 questions or so. I'm going to give you 3 hours to do it, and you'll have all day next Wednesday and Thursday to do it. So anytime in that 48-hour window. Okay, and you can use both sides of 8.5 by 11 for notes. Plus, you can use as many scrap papers as you want, really, just to work out questions. And then a calculator, periodic table. Okay. So does everybody still have their periodic table from like exam one or something like that with all the names and stuff on there? Yeah, if you do, you can use that. I'm also gonna attach a blank one, as I'll see how to attach that to the actual exam. As I don't know if I do it as a separate question or a tab on the lockdown browser or something, but I'll do that as well, so you have it in case you can't find your old one. But yeah, you can use whatever you have as well. Okay. So any other questions? I guess start my video so we can at least have one last shot of seeing each other here. So it's been a pleasure. Um, I wish we were face to face, but I guess it is what it is. And so yeah, let me know if you have any questions. As you're reviewing, if you want to know if something is going to be on or whatever, just let me know. Um, But other than that, yeah, just go through your PowerPoints, your notes, rewatch these videos that are now on YouTube, and and that should be it. Yeah, all of the past practice midterms are still available for you to work on. So I think I didn't do this yet. That reminds me, actually, I will post an optional. It's not going to count toward your homework grades, so don't feel compelled to do them. But it'll help you prep for the exam. Um, I'll just post a few questions related to these energy calculations, as well as the stuff that you haven't been tested on yet. So I think that's like intermolecular forces and energy calculations. So I'll post a few questions on Blackboard and do them if you want. If you don't worry about it. But I'll pull a few extra questions as I'm making up your exam today, and just give you that practice as well. Okay. So all the best to everybody, and study hard. And I guess when we're back on campus, stop by, chat sometime. I'd like to see you guys again. So. All the best. Stay healthy. Have a great summer. If I don't correspond with you before then. So.